So as promised, guys, here's our first Panapto lecture, and I've titled the lecture, Why Are Radicals So Rad? Alright, why are they so cool? So first let's just do a quick review, okay? You should already know quite a bit about this. You've watched the Learn Smart lectures. You've hopefully already taken your quiz. You can use these Panapto lectures however you choose. You can use them as a review for your exam. You can use them as a quick review before you take your quiz, however you'd like. But let's see what you remember, okay? So first things first, we already know that a radical itself is a molecule, is an intermediate that's a single unpaired electron. So we know that, right? We know that it's a single unpaired electron. So here's an example of a carbon radical, right? And there might be a few characteristics of a radical. So let's do this. Go ahead and answer this question really quick and pick all that apply to a radical. Which ones actually describe a radical? Go ahead, take a few minutes and click in all that apply of which descriptions apply to a radical. Good, so hopefully if you've answered this, what we've realized is that if we look at a radical, we think, well, is a radical electron rich or is it electron deficient? Well, hopefully you answered both, right? It is electron rich because there's an electron there ready to do chemistry, and it's also electron deficient, right? Because there's missing one electron to complete its octet, right? So that's one characteristic of a radical. Another characteristic we know about a radical is that they are very reactive, right? They're very reactive intermediates because they are missing that one electron to complete their octet, so we know that also. And we also know that radicals are generated from what we call homolytic cleavage. So for example, if we had a radical that could be generated from a reaction such as this, where we had a bromine here, what we would imagine is that that carbon-bromine bond can be broken homolytically, homo meaning the same, so that we can get two radicals that are generated, right? So few characteristics there, and there are others that I'm not going to go over, but you probably have already learned through Learn Smart, right? So just some different characteristics here of a radical. So now let's get down to the interesting things. Well, why are radicals so rad? Why are they so cool? So the other thing is, well, let's before we go into that, let's ask ourselves another question, because this type of chemistry that I've just demonstrated here doesn't happen spontaneously, right? It just doesn't happen on its own. It has to be stimulated in one fashion or another. So with that said, what type of factors initiate a radical reaction, right? What type of conditions initiate a radical reaction? So take a few minutes to answer that question. And let's go ahead and pick all that apply here also. All right, so if you've answered that question, then, and the question here was, what conditions initiate a radical reaction? Well, so reaction conditions for radicals well, one of them is heat, right? Heat can initiate a radical reaction that we can symbolize with this delta symbol here. Another one is light, right? Light, can, and specifically UV light, can initiate a radical reaction. We symbolize that with this symbol here. And the other one are radical initiators, right? Radical initiators, such as peroxides or AIBN, right? So these are different types of molecules or compounds that can initiate a radical reaction. So now let's get down to that question. Why are radicals so rad? Well, if you think about it, let's think about some real-world application. I don't know if many of you have heard of what we call CFCs, right? chlorofluorocarbons. So here's an example of a CFC. So chlorofluorocarbons. So here's an example. Now CFCs were very commonly used about back in the 1950s, and they were used in refrigerants and cooling systems. But what they found out is that these have been banned from being used in aerosols and coolants and refrigerants for a specific reason. Because when these get released into the atmosphere, they come into contact with UV light, right, from the sun. And we end up generating more radicals because we end up breaking a carbon-chlorine bond, again, homolytically, to generate two radicals. You say, well, what's the big deal with that? Well, what can happen is that this chlorine radical can react with something in the atmosphere that we call ozone, right? And what can happen here is we end up breaking up ozone into another oxygen radical and oxygen gas, right? Well, you ask yourself, we say, well, Dr. Ladd, why is that so bad? I mean, we just made more oxygen, and oxygen's good. We need oxygen, right? Well, hopefully you can see why this would be a bad thing because of what we call the ozone layer, right? The ozone layer here. This is one of the primary reasons that we have caused the depletion of the ozone layer, which were CFCs. And again, these were initiated by UV light. So interesting characteristic there, right? Now, so you say, okay, well, fine, Dr. Ladd, ozone, but I hear it's getting better. Sure, yeah, it's getting better since we banned these. But okay, so I get it. You want something that's a little bit more applicable. Okay, fine. Well, there's another. How many of you think, so if we know that these reactions are facilitated by UV light or heat or peroxides, well, there was another application that I thought was pretty interesting, right? So I was at my dentist, and for some reason my dentist doesn't really like me very much. I think it's because I probably asked too many questions, and I didn't have a cavity, but I needed to put like a little sealant on my teeth because there was some really deep grooves in my teeth, and I noticed that he was putting this liquid in the grooves. And then he got this light, and this is kind of, here's an example of what I'm talking about. He got this light here and started shining this on that liquid. And then so as he had this in my mouth, I'm like, is that a radical reaction? Right? As he had this in my mouth. And he's just like, what are you asking me here? And I said, is that a radical reaction that you're doing right now? And he's like, I don't know, like what that's like, but what do you put in my? He's like, it's a liquid polymer. I said, so what's the light doing? I said, he's well, it's gonna make it solid. I said, but how? So I don't know. I said, like, well, can I see the box of what you're putting in my mouth? Can I see what it is? And eventually what I found out is, yeah, what he was doing was he was initiating a radical polymerization reaction in my mouth, right? He was, by that liquid that he had put in my teeth, by shining the light, he initiated a reaction that would turn that liquid, that bounding agent, into a solid through a radical polymerization reaction, which was pretty cool, right? But he didn't think so. I thought it was really cool. So then, so I said, okay, then no, another application for radical chemistry. So then I thought, okay, what else? What's another? I was, getting my. I decided this was before COVID, right? I decided to go get a pedicure, and guys, don't judge because you probably need one too, right? So I decided to go get a pedicure, and as I was getting a pedicure, I was noticing that there were some ladies that were getting their nails done. And when they were getting their nails done, they were putting their hands in something like this. And what I later learned is that they were doing this, and my students taught me what they were doing. There's something called shellacking. They basically put it in the UV light. And I said, what's going on there? And the lady's like, I don't know. It's gonna make the whatever they put on their nails a little bit more tough, right? A little harder. And again, I said, this must be a radical reaction, right? So of course nobody knew what I was talking about. But again, I'm pretty sure that this must have been another radical reaction, more specifically a radical polymerization reaction, right? So yes, there's a lot of practicality in the way we use radicals in everyday life, right? But just like radicals can be useful, they can also be harmful, right? So there are, let's see, my biology colleagues, let's see if you know, how many of you have heard of what we call ROS species, right? These are called reactive oxygenated species. These are common in your body, and when we get into biochemistry, we'll talk about this. These are very reactive oxygen radicals in your body. And what can happen is when you have a large amount of these in your body, what can happen is they cause cell damage. They cause cell damage, and in some cases, they can also cause cell mutation, right? So they literally interact with the DNA, manipulating that DNA, and then can cause damage and can also cause mutation. So there's a lot of research that goes into trying to limit the amount of reactive oxygenated species in the body. And I wonder how many of you have heard that if you were to eat a certain amount of blueberries, a handful of blueberries every day, that will lower your risk of getting cancer. I wonder how many of you have heard this. Well, the reason for this is because blueberries are very high in an antioxidant, right? An antioxidant, which is called vitamin E. It's very high in an antioxidant called vitamin E. So what is essentially a vitamin E? Vitamin E is actually a radical inhibitor, right? So it can actually inhibit radicals. So the idea here is that by increasing the amount of vitamin E in your body, and you eating blueberries, which are very rich in vitamin E, it can lower your risk of getting cancer. At least that's what the thought is behind that, right? Now, there's another process that is responsible that radicals is responsible for, and people spend hundreds, if not thousands of dollars on this a year. This is a perfectly natural process that that happens that is caused by radicals, but people try to prevent it from happening, and they'll spend a lot of money every year doing that. What do you think that is? Yeah, that's aging, right? Aging. And what do I mean by this? Well, I know a lot of people, I have a lot of people, I might be one of them. There's a lot of people that they'll spend a lot of money on these creams for their face to prevent wrinkles and aging, anti-aging creams, right? So anti-aging creams. So these are very common products that are sold. There's a lot of money that's made in this, right? And they say, okay, just put a little bit on your face and rub it in. And so what people do is they just dip their whole face in it, right? And say, nope, I'm not aging at all. Well, if you think about it, it says, well, what are the anti-aging things that are probably in here? So I looked at the back of a bottle, and what I noticed is they're very high in vitamin E, right? So they're very high in vitamin E again. So why? Again, radical inhibitors, right? So because of that aging process, cell damage, cell decay, this vitamin E can reduce the reactive oxygenated species that cause this, and can also be used as an anti-aging cream. So again, a lot of cool radical chemistry here, and I hope now that you understand why radicals are so rad.